1st March 1943, 03:47 hours, 200 miles west of the Bay of Biscay. A Vickers Wellington bomber of RAF Coastal Command drones through the darkness at 1,200 feet, its twin Bristol Pegasus engines throbbing steadily against the black Atlantic void below. Inside the cramped fuselage, Flight Lieutenant James Walker monitors a cathode ray tube barely larger than a dinner plate, its greenish glow illuminating his face with an eerie phosphorescence. The screen shows nothing but electronic snow and the faint sweep of a rotating cursor. Then, without warning, a bright point of light appears at the edge of the display. Walker leans forward, his pulse quickening. The contact is sharp, unmistakable, and 9 miles distant. He keys the intercom. Contact bearing 047 degrees, range 9 miles, moving left to right. The pilot banks gently, bringing the Wellington onto an intercept course. Nobody aboard the aircraft speaks. They have done this before, but the technology they are using is so new, so revolutionary, that each successful detection still carries the thrill of the impossible made real. The submarine below has no idea it has been seen. Its commander stands on the conning tower, scanning the horizon with binoculars, confident in the protective cloak of darkness. His METOX receiver, designed to detect radar emissions, remains silent. As far as he knows, he is invisible. The Wellington descends to 500 feet. At 2 miles, Walker can see the submarine's wake on the scope, a ghostly trail in the radar return. At 1 mile, the pilot spots the telltale phosphorescence of disturbed plankton, marking the U-boat's passage. He drops lower still, throttles wide, racing toward the target. The submarine's lookouts finally hear the aircraft engines, but it is far too late. 6 depth charges tumble from the Wellington's bomb bay, their casings glinting briefly in the bomber's landing lights. They bracket the submarine perfectly. The sea erupts in 6 towering columns of white water. When the spray settles, the U-boat is gone, broken in half by the precision of the attack. The entire engagement, from first detection to destruction, has taken just 12 minutes. The sinking of U-boat 465 that March morning exemplified a technological revolution that fundamentally altered the character of the Battle of the Atlantic. For 3 years, German submarines had operated with near impunity under cover of darkness, surfacing at night to recharge batteries and transit at higher speeds whilst remaining effectively invisible to Allied aircraft and surface vessels. The mathematics of the problem were brutal. A surfaced U-boat presented a target barely 3 meters high and perhaps 50 meters long. At night, even in moonlight, visual detection beyond 2 or 3 miles was essentially impossible. By the time an aircraft crew spotted a submarine visually, the U-boat's lookouts had almost invariably heard the engines first, giving the crew precious seconds to crash dive. Aircraft equipped with searchlights fared little better. The Leo light, whilst effective, required the aircraft to descend to dangerous altitudes and gave the submarine advance warning of the approach. The existing radar technology compounded rather than solved the problem. Early air-to-surface vessel radar, operating on wavelengths of 1.5 meters, could detect a surfaced U-boat at perhaps 10 to 12 miles under ideal conditions. The challenge was that U-boats could detect these transmissions at far greater ranges using simple receivers. The Germans had developed the METOX detector, a crude but effective device that picked up the meter-wave radar emissions and gave submarines ample warning to dive before an aircraft could close to attack range. The asymmetry was devastating. Allied aircraft could search vast areas, but rarely caught U-boats on the surface. The submarines, warned by their receivers, simply submerged and waited for the aircraft to pass. When aircraft did achieve surprise attacks, the results were dramatic, but such incidents were remarkably rare. The statistics told a grim story. In the first 3 months of 1943, German U-boats sank 97 Allied merchant ships totaling over 500,000 tons. During the same period, Allied forces sank just 15 submarines. The exchange ratio was unsustainable. Britain imported 68 million tons of supplies annually. At current loss rates, the Atlantic lifeline would be severed within months. The Admiralty calculated that to maintain supply lines, they needed to reduce shipping losses by at least 60%, whilst simultaneously tripling the rate of U-boat destruction. Conventional approaches had reached their limits. More escorts, more aircraft, better tactics, all helped marginally, but none addressed the fundamental problem. Submarines could hide in the darkness, and existing technology gave them advance warning of approaching threats. The solution emerged from a deceptively simple principle. If radar could operate on shorter wavelengths measured in centimeters rather than meters, it would be far more difficult for submarines to detect, and the shorter wavelength would provide dramatically improved resolution and range discrimination. The physics were straightforward. The engineering was anything but. Creating a radar transmitter that could generate sufficient power at wavelengths of 10 centimeters or less required a component that simply did not exist in practical form: the cavity magnetron. The magnetron had been understood theoretically since the 1920s, but producing one that could generate useful power at centimetric wavelengths had defeated engineers for 2 decades. The breakthrough came at the University of Birmingham in February 1940, when physicists John Randall and Harry Boot constructed a cavity magnetron that produced an astonishing 400 watts of continuous power at a wavelength of 9.8 centimeters. Within months, they had improved the design to produce kilowatt-level pulses. The device itself was elegantly simple in concept: a cylindrical copper block with precisely machined cavities surrounding a central cathode, all within a powerful magnetic field. When energized, electrons spiraled through the cavity structure, generating electromagnetic oscillations at frequencies determined by the cavity dimensions. The precision required was extraordinary. The cavities had to be machined to tolerances of a few thousandths of an inch, and the magnetic field had to be precisely calibrated. But once perfected, the magnetron could generate radar pulses at 10 centimeters wavelength, with peak powers exceeding 10 kilowatts, all from a device small enough to hold in one hand. The strategic implications were immediately apparent. A 10-centimeter radar could detect a submarine at similar or greater ranges than existing meter wave sets, but the U-boat's METOX receivers, designed for much longer wavelengths, would be completely blind to the emissions. Moreover, the shorter wavelength provided far superior resolution, allowing operators to distinguish between genuine targets and sea clutter or false echoes. The challenge was not simply building the magnetrons, but deploying them operationally before the Germans could develop countermeasures. The development program moved with extraordinary urgency. The Telecommunications Research Establishment at Swanage designed a complete airborne radar system designated ASV Mark III. The radar operated at precisely 9.7 centimeters, used a rotating antenna beneath the aircraft's fuselage, and featured a plan position indicator display that showed contacts as bright points on a circular screen. The entire system, including transmitter, receiver, display, and antenna, weighed approximately 300 pounds and consumed 500 watts of electrical power. Production began in late 1941, with initial sets fitted to Wellington and Liberator aircraft of Coastal Command. The first operational deployment occurred in March 1943, deliberately timed to coincide with a renewed U-boat offensive in the North Atlantic. The Germans had massed 42 submarines in 3 patrol lines across the convoy routes, anticipating heavy kills as spring weather improved. Instead, they encountered catastrophe. Aircraft equipped with ASV Mark III hunted surfaced U-boats with devastating effectiveness. On the night of 28 February, Squadron Leader Wilfred Olton detected U-boat 632 at 11 miles range, closed unseen, and destroyed the submarine with a single stick of depth charges. Within 2 weeks, Coastal Command aircraft had sunk 7 U-boats and damaged another 12 using the new radar. The U-boat crews were baffled. Their METOX receivers gave no warning. Aircraft appeared suddenly from the darkness, launched perfect attacks, and vanished before the submarines could even man their anti-aircraft guns. The German response reveals both the effectiveness of the new radar and the limitations of technological intelligence in wartime. U-boat command initially assumed the Allies had developed an infrared detection system, perhaps tracking the heat signature from diesel engines. Submarines received orders to reduce engine exhaust temperatures and to spend more time submerged, measures that reduced operational effectiveness but did nothing to counter the actual threat. Some German engineers suspected radar, but on shorter wavelengths than anyone had thought practical. The Kriegsmarine began developing receivers sensitive to 10-centimetre emissions, but the program moved slowly, hampered by competing priorities and skepticism about whether the British could actually produce centimetric radar in operational quantities. The production statistics demonstrated precisely what British industry could achieve when properly motivated. By June 1943, factories were producing 150 cavity magnetrons per week. Each magnetron cost approximately £40 to manufacture, a trivial sum compared to the value of the merchant ships it would help protect, or the U-boats it would help destroy. The radar sets themselves, including installation, cost roughly £3,000 per aircraft. Coastal Command operated approximately 300 long-range maritime patrol aircraft at peak strength, meaning the entire fleet could be equipped for under £1 million, equivalent to the cost of perhaps 6 merchant ships. The return on investment was extraordinary. Between March and May 1943, aircraft equipped with ASV Mark III accounted for 41% of all U-boat sinkings, whilst representing only 18% of Coastal Command's operational strength. The tactical revolution extended beyond simple detection. The centimetric radar allowed aircraft to vector surface escorts onto submerged submarines with unprecedented precision. An aircraft detecting a U-boat could track it visually or by radar until it dived, then guide destroyers or corvettes to the diving position within minutes. The submarines, accustomed to escaping by submerging and moving away from the last known position, found themselves under immediate and sustained attack. The radar also enabled what became known as cooperative searches, with multiple aircraft coordinating their patrol patterns to blanket entire ocean areas. A single Wellington could effectively search a corridor 20 miles wide. 3 aircraft in formation could monitor 60 miles of ocean, making it nearly impossible for a surfaced U-boat to transit undetected. The impact on U-boat operations was catastrophic. In May 1943, the Kriegsmarine lost 41 submarines, the highest monthly total of the entire war. Admiral Karl Dönitz, commander of the U-boat arm, withdrew his forces from the North Atlantic convoy routes on 24 May, conceding temporary defeat. In his war diary, he wrote, "The enemy has succeeded in gaining the advantage in submarine defense. The reason for this is, perhaps, a new location device with which the boats cannot fight." It would be another 6 months before German intelligence definitively identified centimetric radar as the culprit, and by then the technological advantage had become insurmountable. The Allies extended the radar technology across multiple platforms and wavelengths. Naval vessels received centimetric surface search radars that could detect periscopes at several miles range. Smaller 3-centimetre sets, even more difficult to detect, and with superior resolution, equipped later aircraft variants. The Americans developed their own versions, using slightly different frequencies, but based on the same Magnetron technology. By 1944, virtually every Allied aircraft and major surface vessel in the Atlantic carried centimetric radar. The oceans had become transparent to Allied technology, whilst remaining opaque to German sensors. German attempts to counter the threat evolved through several phases, none entirely successful. The Naxos receiver, introduced in late 1943, could detect 10-centimetre radar at ranges up to 30 miles. But by that time, many Allied aircraft were using 3-centimetre sets, to which Naxos was blind. The submarines received upgraded anti-aircraft armament, with some boats carrying 2 quad 20mm cannons and a 37mm gun, but fighting back on the surface simply exposed the U-boat to air attack for longer periods. Schnorkel devices, allowing submarines to run diesel engines whilst remaining submerged, reduced surface time but cut transit speeds from 17 knots to 6 knots, drastically reducing operational radius and patrol effectiveness. Acoustic torpedoes designed to home on escort vessel propeller noise achieved some successes but came too late and in too few numbers to alter the strategic balance. The technological race extended to wavelengths the human eye could not see. British aircraft began carrying infrared detectors that could spot the heat signature of a recently submerged submarine, giving away its position even after diving. The Germans experimented with radar-absorbent coatings and coated their schnorkel heads with synthetic rubber impregnated with carbon, reducing but not eliminating radar returns. Each measure prompted a countermeasure. The Allies varied radar frequencies randomly across a range of wavelengths, making it impossible for a single receiver to provide reliable warning. They developed signal processing techniques to filter out sea clutter whilst enhancing genuine targets. They improved antenna design to provide narrower beams and better bearing discrimination. The submarines, designed for a war of stealth, found themselves increasingly visible to technologies they could neither detect nor evade. The broader strategic implications reverberated beyond the Atlantic. The cavity magnetron enabled ground-based radar systems of unprecedented resolution, allowing RAF night fighters to intercept German bombers with devastating effectiveness. The same technology provided naval gunnery radars that could track targets through smoke, darkness, and poor weather. American bombers used magnetron-based radar for blind bombing through cloud cover. The physics department at Birmingham University had delivered a component that influenced virtually every aspect of the electronic war. The human cost of the technological advantage is impossible to calculate precisely, but undoubtedly ran to thousands of lives. Each U-boat sunk represented perhaps 50 German sailors killed or captured. But each U-boat prevented from sinking, merchant ships represented hundreds of merchant seamen who survived the war, thousands of tons of supplies delivered safely, and a strategic position maintained that might otherwise have collapsed. The counterfactual question, what if Britain had not developed centimetric radar, suggests an answer too grim to contemplate. Without the magnetron, the Battle of the Atlantic would likely have continued through 1943 and 1944, with mounting Allied shipping losses, forcing reductions in supply convoys to both Britain and the Soviet Union. The invasion of Europe might have been delayed or become impossible. Strategic bombing campaigns would have faltered for lack of supplies. The entire Allied war effort rested on a thin margin of available shipping, and that margin depended critically on keeping U-boat sinkings within sustainable limits. The post-war assessment by the United States Strategic Bombing Survey concluded that the introduction of centimetric radar marked the decisive turning point in the Battle of the Atlantic, more significant than any other single technological development, including escort carriers, long-range aircraft, or improved depth charges. The German naval staff's own analysis agreed, noting that the 10-centimetre radar rendered obsolete all previous methods of submarine warfare. The numbers support these conclusions. In the 20 months before March 1943, Coastal Command aircraft sank 45 U-boats. In the 20 months after March 1943, they sank 188. The difference was not more aircraft or better tactics, although both helped. The difference was that submarines could no longer hide in the darkness. The legacy of the cavity magnetron extends far beyond its wartime applications. The same physics that enabled centimetric radar made possible the microwave ovens that would transform domestic cooking, the telecommunications systems that carry modern telephone and data traffic, and the radar systems that guide civilian aircraft and monitor weather patterns. The precision machining techniques developed to manufacture magnetrons advanced the entire field of microwave engineering. The display technology pioneered in ASV, Mark III evolved into the cathode ray tubes that dominated television and computer displays for half a century. The signal processing methods developed to distinguish U-boats from sea clutter became foundational to modern digital communications. Several examples of ASV Mark III equipment survive in museums, including complete installations at the Royal Air Force Museum in London and the Imperial War Museum. The cavity magnetrons themselves, being relatively simple and robust devices, were preserved in considerable numbers. A working Wellington bomber at the Canadian Warplane Heritage Museum carries a reconstruction of the complete radar system, occasionally demonstrated to visitors. Original operators, now in their late 90s or older, occasionally participate in documentary productions, describing the almost magical ability to detect submarines invisible to any other sensor. Their accounts emphasize the psychological impact as much as the technical capability. Knowing they could find submarines in absolute darkness, in any weather, at ranges far beyond visual detection, transformed night patrols from exercises in futility into productive hunts. The technology created confidence, and that confidence translated into aggressiveness and tactical innovation. Recent historical research, including declassified German documents and recovered U-boat logs, has provided additional detail on the German perspective. The confusion and fear among U-boat crews facing an invisible enemy comes through clearly in patrol reports from spring 1943. Commanders describe phantom aircraft that appear without warning, attack with uncanny accuracy, and vanish into the night. Some crews suspected British agents had infiltrated their bases and were transmitting departure information. Others theorized that the Allies had broken German naval codes, allowing aircraft to be positioned precisely along known patrol routes. Both suspicions had some foundation. The Allies had indeed broken the codes, but the real revelation was technological, not cryptographic. The submarines were being hunted by machines that could see in the dark across distances measured in miles, and against such machines the traditional tactics of submersible warfare had become obsolete. The development and deployment of centimetric radar represents industrial mobilization and scientific cooperation at its most effective. From laboratory prototype to mass production in 36 months, from first operational use to theater-wide deployment in 12 months, the program moved with a pace that seems almost inconceivable by modern standards. The urgency of war compressed development cycles and eliminated bureaucratic obstacles. Scientists worked directly with operators, receiving immediate feedback on performance and reliability. Manufacturers received precise specifications and produced equipment that worked reliably under the harshest conditions. The entire system, research, development, production, deployment, and tactical innovation, functioned as an integrated whole, all focused on a single objective: making the Atlantic unsafe for U-boats. The irony, apparent only in retrospect, is that the technology that dominated the Atlantic was never meant for submarine hunting. The original impetus for centimetric radar came from the need to detect aircraft at night with sufficient resolution to guide interceptor fighters. The adaptation to maritime patrol occurred almost as an afterthought, a secondary application of a device developed for an entirely different purpose. Yet this secondary application arguably had greater strategic impact than the primary one. Night fighter radar certainly helped Britain survive the Blitz and later devastated German bomber formations, but centimetric ASV radar helped win the Battle of the Atlantic, and winning the Atlantic made possible everything else the Allies achieved in Europe. 30 submarine wrecks discovered in recent decades show damage patterns consistent with precision air attacks. Depth charges clustered tightly around the hull, indicating the attacking aircraft knew exactly where the submarine was, not merely its approximate position. Archaeological surveys of these wrecks, lying in water too deep for wartime salvage, reveal submarines caught completely unaware, often with hatches still open or anti-aircraft guns unmanned, suggesting the crews never saw or heard the attacking aircraft until weapons were already falling. These underwater grave sites testify to the totality of the technological surprise. The submariners went to sea believing darkness provided protection. They were wrong, and that error killed them. The final accounting of the Battle of the Atlantic shows 783 U-boats destroyed out of 1,162 commissioned during the war. Aircraft accounted for 245 of those kills, surface ships for 246, with the remainder lost to mines, accidents, or combined surface and air action. But these numbers, whilst accurate, obscure the strategic reality. The U-boats did not simply need to be destroyed. They needed to be prevented from sinking merchant ships faster than replacements could be built. This was fundamentally a mathematical problem: the rate of merchant ship construction versus the rate of merchant ship loss. Centimetric radar altered that equation decisively. By making surface transit hazardous and forcing submarines to remain submerged for longer periods, the technology reduced the hunting efficiency of each U-boat by approximately 60%. A submarine that could previously patrol a convoy route for 30 days found itself limited to perhaps 12 days of effective patrol time, spending the rest submerged or transiting slowly on schnorkel. The ocean became larger, and the targets became scarcer. Even U-boats that survived their patrols achieved fewer sinkings per day at sea. The campaign became, from the German perspective, unsustainable, not because U-boats were dying in unsupportable numbers, though they were, but because even the survivors were failing to sink enough ships to matter. The transformation of the Atlantic from German hunting ground to German graveyard rested on many factors: more escorts, escort carriers, improved tactics, better depth charges, code breaking, long-range aircraft, and experienced crews. But the technology that made darkness transparent, that allowed aircraft to find submarines beyond visual range and without warning, that forced U-boats to abandon the surface and crawl submerged across oceans, that technology changed the fundamental character of the battle. The cavity magnetron, a device small enough to fit in a coat pocket, broke the U-boat offensive more decisively than all the destroyers and corvettes combined. In museums across Britain and North America, examples of ASV Mark III equipment sit in climate-controlled displays, their cathode ray tubes long since dark, their magnetrons cold and silent. Visitors, if they pause to read the placards, learn that this equipment helped defeat German submarines. What the placards cannot fully convey is the intellectual audacity required to imagine that such a device could work, the engineering precision required to make it work reliably, the industrial capacity required to produce it in thousands, and the tactical innovation required to use it effectively. The technology succeeded not because it was complex. The magnetron was elegantly simple in principle, but because it was precisely engineered, properly deployed, and matched to a genuine strategic need. The night sky above the Atlantic no longer echoes with the throb of Wellington bombers hunting submarines in the darkness. The U-boats rest on the ocean floor, silent monuments to a campaign fought and lost. But the principle demonstrated in those desperate months of 1943 remains valid. In technological warfare, seeing the enemy whilst remaining unseen provides an advantage so fundamental that it can overcome numerical superiority, tactical skill, and operational experience. The Battle of the Atlantic was not won solely by courage or numbers or industrial output, essential though all these were. It was won in significant measure by physicists who understood electromagnetic waves, by engineers who could machine copper to thousandths of an inch, and by tacticians who recognized that a hand-sized component could transform an entire theater of war. The centimetric radar turned the Atlantic into a death trap for U-boats, not through destructive power, but through visibility, making the hunter visible to the hunted. And in that reversal of perception lay the difference between strategic failure and strategic victory.